So in this problem, we have a spring, and we want to compress the spring some displacement x. We want to compress it, so push on it a little bit, to store 20 joules of energy, okay? If the stiffness constant is 85 newtons per meter, how far do we have to go to store 20 joules of energy? Well, this requires a formula here that entails of elastic potential energy. What is elastic potential energy equal to? Well, we know that that is 1/2 k x squared. Not to be confused with the restoring force, which is equal to negative xk. Okay, this is different. This is, okay, how much energy are we storing in that spring? And that's given by this equation here, the displacement squared times 1/2 of the stiffness constant. So let's do this here. We know that potential energy is stored in joules, and that's exactly what we're looking for. So we are actually looking for the potential energy elastic for 20 joules. So we'll plug that in here. It's equal to 1/2 times k, which is just that constant that tells us how that spring is relative to other springs and its stiffness. Okay, fair. And now we need to find x squared, the displacement. So it's just a simple plug and chug from here. I mean, so we bring over, or we can actually take 1/2 of 85 first. So give me a second. This comes out to 42.5 newtons per meter, so we take 20.0 joules over 42.5 newtons per meter. And just so we make sure that all of our units are canceling, because when you do these problems, if you ever think you're doing something wrong, check to see if your units are messed up. That's a common place that people mess up pretty bad. I'll actually bring the problem over here quick, so take a gander if you want, if I'm blocking anything with my body. I want to express the joules as a full unit. Okay, so we know that our 20 joules is really equal to 20 Newton meters, because a joule is a Newton meter. We can express a Newton as a kilogram meter per second a second, right? We times by the meter because it's in Newton meters. We get kilograms meters squared over seconds squared. Okay, we divide that by the 42.5 Newton per meter, right? What does that do to the Newton, right? If Newton is kilogram meters per second squared and we divide it by a meter, well, that just cancels out the meters there, and we're left with kilograms per second. So, dropping my cap. So really, we could just write this as kilograms per second a second. And I know this might be a little confusing, but it's important to see how the units kind of play out, right? Notice how we have kilograms per second top and bottom. So you can actually cancel out kilograms and the seconds, and we're left with meters squared. That's a good thing because we have a x squared, and if we take the square root, we get meters. That would be displacement, so important fact there. What is 20 divided by 42? Great question, I have no idea. Let's figure it out. We're gonna get that this is equal to 8/17 meters squared is equal to x squared. So our displacement is equal to, and that's not mass, please don't confuse that, I apologize. It can come across that way. The square root of 8/17, right? If we want to get rid of the square, we take the square root. We get that simply the meters is, geez Louise, what am I doing? 2/30, square root of 34/17 meters equals x, which is approximately equal to 0.686 meters is how much we have to compress. So if we want to compress that spring, bring it down to this and store 20 joules of energy, given that our stiffness constant is this, we need to compress it by 0.686 meters. Hope you guys enjoyed, and I hope you found this lesson helpful. If you did, please drop a like and subscribe. Comment if you have any questions, and have a wonderful day.